In this video, we're going to be looking at 3 different examples of nucleophilic substitution reactions. We'll be defining a nucleophile and explaining why hydroxide, cyanide and ammonia behave as nucleophiles, and then also describing what a nucleophilic substitution reaction is and how the mechanism for those reactions work. In the previous videos in this series, we've met the halogenoalkanes or haloalkanes, and these are molecules in which one or more of the hydrogens in an alkane has been replaced by an atom from group 7. We've also described how these halogenoalkanes can be primary, secondary or tertiary, depending on the location of that substituted atom. And we've also mentioned that the bonds between carbon and those halogens are highly polar due to the higher electronegativity of the halogens. Now this is important because it's those polar bonds that allows a halogenoalkane to be attacked by a nucleophile. You'll remember from your bonding topic that in a polar bond, the electrons that are shared in that bond are not perfectly in the middle. Instead, they're pulled slightly towards the more electronegative element. And so this causes it to become slightly negatively charged. And we show this very slight negative charge using a lowercase delta. Now, depending on the rest of the structure of that molecule, it's possible that the whole molecule becomes polar or that it doesn't. If the molecule is symmetrical, like this tetrachloromethane, then actually the molecule won't be polar because even though the individual bonds are polar, they're all kind of balancing each other out. So this molecule is essentially slightly negative the whole way around the outside and slightly positive in the centre. So overall, there isn't sort of a negative side of the molecule and a positive side of the molecule. Whereas in this water molecule, we do have that negative side where the lone pairs for the oxygen are, and then the slightly positive side where the hydrogens are. So just to make sure you've remembered what we're talking about here, just pause the video and identify which of these molecules does not have a permanent dipole. The answer, of course, is the last one, because this is the one in which we have 4 of the same type of bond as they're all cancelling out because it's a symmetrical molecule. So on to the new stuff. Halogenoalkanes undergo substitution reactions with nucleophiles, and there are 3 named examples here. Hydroxide and ammonia you're already quite familiar with, but the new one will be the cyanide ion. It's important to note that all 3 of these species have a lone pair of electrons, and also that both hydroxide and cyanide have got negative charges. But what actually is a nucleophile, and what is a nucleophilic substitution reaction? Well, literally, a nucleophile is something that is attracted to the nucleus. And this is going to be because it has a lone pair of electrons that it is able to donate. And when it does this, it's going to take the place of part of the molecule. So now we know what a nucleophile is, which one of these 4 could act as a nucleophile? Well, this is going to be a little bit easier to get our heads around if we actually have some pictures. So I'm going to draw them out quickly. So we've got methane, ammonium, phosphine, and borane. So you can see that in methane, all of the electrons from carbon are tied up in bonding pairs. Likewise, in our ammonium ion, all of the electrons are tied up. So don't get confused about the fact that ammonia can be a nucleophile, because this is actually a different ion. It's picked up an extra H+, and so there are no electrons left over. But phosphine is looking a bit more hopeful, because you can see that we've got that lone pair there. So that's going to be our correct answer. Now, before we start looking at the mechanisms for these 3 substitutions, let's talk quickly about the polarity of those bonds in these halogenoalkanes. We've already said that the bond between the carbon and the halogen is extremely polar. Well, fluorine is the most electronegative element in the whole periodic table, and that means its bonds are incredibly polar, and that's going to make them stronger. So this means that fluoroalkanes don't react at all, whereas iodoalkanes react very rapidly. So bearing in mind what we've just said about the strength of the bonds, which one of these rows is true? We said on the previous slide that fluoroalkanes don't react at all. That's going to be our slowest one. So as we work our way down group 7, things get faster and faster. So straight away we can say that our answer is going to have to be either A or B, because iodoalkanes are going to react faster than bromoalkanes. So then we need to look at our reason. If it's reacting fastest, it's going to be because the bond is weakest. So therefore our correct answer is going to be B. So before we start thinking about specific nucleophilic substitution reactions, let's just look at the general process. So we're always going to have a halogenoalkane. So there's a halogen group, which could be fluorine, although realistically we know that fluoroalkanes are very unlikely to react, so it's much more likely to be chlorine or bromine or iodine. You might also be given a molecule in which we refer to the R group, and that just means the rest of the molecule. You don't need to worry about it. You might have an R group, or you might actually have the rest of the alkane drawn out. Either way, it's not going to take part in this process. Now, because this is a nucleophilic substitution reaction, we have a nucleophile, and this can be represented as Nu. And you can see here it's really important that my nucleophile has got a lone pair, because otherwise it wouldn't be possible for this reaction to take place. And in a nucleophilic substitution reaction, the nucleophile is going to take the place of the halogen. So now the nucleophile is part of what was the halogenoalkane, and we've got this halide ion being kicked out, and we refer to this as the leaving group. There are a couple of other things that you should be aware of before we start drawing these mechanisms. The first one is that these arrows represent electrons. So here it's an electron pair, and therefore it's going to be a double-headed arrow. And that arrow is going to go from the electron pair to wherever it's going. So if I've got a hydroxide nucleophile like this, then my arrow should be going from that lone pair, which is on the oxygen. It should never be going from the hydrogen or from a different bit of the oxygen that wasn't the lone pair. Now, for our halogenoalkanes, in order to know where that nucleophile is going to attack, we need to know where there is a region of positive charge. So I'm going to put a delta positive on my carbon to show it's slightly positive, and a delta negative on my fluorine to show that it's slightly negative. So we've got this polar bond. And of course, electrons are negative, so my electrons are going to attack that slightly positive carbon there. Our first example of a nucleophilic substitution reaction is going to involve breaking a chemical bond using a hydroxide ion. So it's an example of a hydrolysis reaction. And here is the halogenoalkane that we're going to break apart. So pause the video and write down what it's called. If you said chloroethane, then you're right. Remember, when we've only got one substitute group and we've only got ethane, we're not going to have any numbers, because whichever carbon I put it on, I would still just call it chloroethane. The first thing I'm going to do when I'm drawing this mechanism is that I'm going to make sure that my nucleophile has got a lone pair on it. And then I'm going to mark up my carbon-halogen bond to show that the carbon is slightly positive and the halogen is slightly negative. So then I'm going to draw my first arrow, and remember it's going to go from the lone pair of electrons to the slightly positive carbon. What's going to happen then is that this bond between the carbon and the halogen is going to break, and both of the electrons from that are going to be taken by the chlorine, which is our leaving group. So my second arrow goes from the middle of that bond to the chlorine to show that it's accepting both of the electrons. And then my products are going to be some ethanol, which is an alcohol, and then also this chloride ion. Let's have a look at another example. So here's our halogenoalkane. Pause the video and write down what you think it's called. Hopefully you identified that this was 2-bromopropane. Once again, I'm going to start off by making sure that my nucleophile has got a lone pair, and that I've marked up my carbon-halogen bond with a delta positive on the carbon and a delta negative on the halogen. So my first arrow is going to go from that lone pair to the delta positive carbon, and then the bond between the carbon and the halogen is going to break. So my second arrow is going from the middle of that bond to the bromine, and my products are going to be some propan-2-ol and a bromide ion as my leaving group. A more typical phrasing for an actual exam question would ask you to outline the mechanism for the nucleophilic substitution reaction of 1-iodopropane with sodium hydroxide. So the first thing I need to do is draw my 1-iodopropane, and like I keep doing, I'm going to add those delta positive, delta negative signs to the carbon-halogen bond. Then I'm going to add in my hydroxide ion, making sure that it's got a clear lone pair. My first arrow is going to go from that lone pair to the delta positive carbon, and my second arrow is going from the middle of that carbon-iodine bond just to the iodine. Then I can draw my products, which here are going to be propan-1-ol and that iodide leaving group. Now, hydroxide ions can and do act as a nucleophile and undergo substitution reactions, but also hydroxide ions can act as a base, in which case the reaction is a different type of reaction called an elimination reaction. Now, we're not going to worry about elimination reactions yet, but you do need to know which reaction conditions will promote substitution instead of elimination. So the first thing is that substitution is too slow at room temperature, and therefore the reaction needs to be warmed. The second thing is that being in aqueous solution promotes substitution. But halogenoalkanes won't dissolve in just water, so it also needs to be slightly ethanolic, and that ethanol is going to act as a solvent. We also need some hydroxide ions, so typically we use potassium or sodium hydroxide. Also, the type of halogenoalkane that we're using is also going to have an impact on whether we see substitution or elimination. So primary halogenoalkanes are more likely to undergo substitution reactions than secondary, which are more likely to undergo elimination reactions. Tertiary halogenoalkanes will do both. Now we're going to move on to substitution with cyanide ions. So again, here's a halogenoalkane. Pause the video and write down what you think it's called. If you said chloromethane, then you're right. The mechanism for substitution with a cyanide ion is basically exactly the same as with a hydroxide ion, just we get different products. And the nice thing about doing substitution with a cyanide ion is it's a good way to add an additional carbon onto your carbon chain. So we're going to go through exactly the same process, starting with a lone pair on our nucleophile and drawing a curly arrow that goes to the delta positive carbon. Then from there, we're going to do a second arrow that goes from the middle of the carbon-halogen bond to the halogen. But of course, we're going to make different products compared to the hydroxide. So here, we're going to make ethane nitrile, which is a type of nitrile, and we'll worry more about them later in the course. But you might be thinking, well, how can it be ethane when we started with methane? But of course, we've just added in a carbon from our cyanide, so that's why it's F. You might also hear this molecule referred to as methyl cyanide, which is a valid name for it, but it's not the nomenclature system that AQA use. In order to undergo substitution with cyanide ions, again, we want it warm, aqueous and alcoholic, but also we're going to have potassium cyanide instead of potassium hydroxide. We've got one more type of substitution reaction to look at, so pause the video and write down what you think this halogenoalkane is called. If you said bromoethane, then you're right. Our final nucleophilic substitution mechanism is going to be with ammonia, and this is a little bit more complicated because whereas with the hydroxide and the cyanide ions, it was a single step process and we just had our starting species and our end species, this is going to be a multi-step process and we're going to need to draw some intermediates. The mechanism starts in exactly the same way. The lone pair on the nucleophile is going to attack the delta positive carbon, and then both of the electrons in the bond between that carbon and the halogen are going to be donated to the halogen atom. So we still get our bromide ion leaving group, but rather than being left with a neutral molecule, we're left with a cation. And if you think about it, this makes sense. We started with two neutral molecules, so at the end of this process, we still have to have overall neutral charge. So if we're losing an anion, we must be left with a cation. And you'll notice that this isn't a delta positive because we're not talking about just a tiny, tiny amount of charge. It is a full-blown charge. So that positive charge on one of the hydrogens bonded to that nitrogen is going to attract another lone pair from another nucleophile. So we actually need two molecules of ammonia for this process. So again, that lone pair is going to be attracted to something that is positively charged. And then what's going to happen is the nitrogen is going to withdraw the electron density from that bond. So we're going to have another arrow that goes from the middle of that nitrogen-hydrogen bond just up to the nitrogen. And so what we're left with is ethyl amine, which is obviously an amine, and also an ammonium ion. Nucleophilic substitution with ammonia is actually a reversible reaction, and that means that unless you have a really dramatic excess of ammonia, which is going to shift your equilibrium to the right hand side, it's very hard to get a pure product. You just get lots of your reaction mixture still in there. So it's really important to have excess concentrated ammonia. It's also important that this is in ethanol rather than in water, because if you have water, then you'll just have some hydroxide ions in there and they will undergo the substitution instead. It's also important that this has to happen under very high pressure, and really the only way to do this is in a sealed tube. You can't heat the mixture under reflux because the ammonia would just escape up the condenser as a gas. Let's check whether you've been paying attention. Which one of these compounds can be formed from chloroethane in a nucleophilic substitution reaction? Pause the video and then come back to me with an answer. Well, let's start off by drawing a quick sketch of chloroethane. So if chloroethane was to undergo a substitution reaction where it was attacked by a cyanide ion, then unfortunately what we would actually get is propane nitrile. So this first option is no good to us because it has the wrong number of carbons in. If we think about our second option where we're attacked with ammonia, then we're going to start off with an intermediate that looks something like this, and then that's going to turn into one of these, which is exactly what we've got. So our correct answer is going to be number 2. And a few more questions. Pause the video and then we'll go through the answers. If we're trying to make a product with 4 carbons and we're starting with chloropropane, which only has 3 carbons, then we need the only nucleophile that we know about that is going to add another carbon to the chain. So it's going to need to be a cyanide ion. If chloropropane reacts with ammonia, then that chlorine atom is going to be replaced originally by the full ammonia molecule and then eventually just by NH2, which is an amine group. So we're going to have propylamine. And if one iodopropane undergoes nucleophilic substitution, then that iodine atom is going to be replaced by the OH from the sodium hydroxide, and so we're going to be left with propan-1-ol. Thanks very much for watching, and I hope that you're now feeling more confident about drawing the reaction mechanisms for nucleophilic substitution reactions. If you did find this useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.